Okay, here we are for the next Zoom. This is Zoom questions for the notes that's going to go from number 75 to 100, I think. This is called scientific notation for fun and personal enjoyment. I could call it just scientific notation, but it wouldn't seem fun and you wouldn't enjoy it. So this is a really cool objective. Scientific notation we're going to use quite a bit in chemistry because there's lots of really, really gigantic numbers. And there's also really small numbers. In red here, this big number, 6.02 times 10 to the 23rd, that actually has a name. It's called Avogadro's number. We'll get to that another day. And that is the number of atoms in a mole of atoms. And that's also the number of molecules in a mole of molecules. A mole is a specific measurement in chemistry, just like a dozen is 12 roses, or a dozen is 12 bagels, or I don't know. This is just another number, right? A pair of shoes is 2 shoes. This is a lot of atoms, but it's a specific scientific number. But the number is so gigantic, we can't write all those zeros, so we write scientific notation. The density of helium. Helium is element number 2 on the periodic table. Helium is very low density. That's why it floats in the air. And the density of helium is listed as 1.64 times 10 to the minus 4th grams per ml. Now, when you have a negative exponent, that means it's a decimal. It doesn't mean that it's a big number. It means it's a very small number. So it would be tenths, hundreds, thousandths. This would be 1.64 10,000ths. It's a really small number. The part of the number in the front, the 1.64 or above the 6.02, that's called the coefficient. In the back part of the number, that's called the power of 10 of the exponent. In our class, always, because we have to always get the right numbers. This is not math where everything can be equal to each other. There's certain rules. In scientific notation, the coefficient, the number in the front, must be greater than 1, but it must be less than 10. And if your math works out, and sometimes it does, the math works out that you might have a 0.164 times 10 to the negative third, you have to adjust it. Or if you have 60.2 times 10 to the 22nd, you have to adjust it because the coefficient must always be greater than 1 but less than 10. Now, these are some giant numbers. Once when I was bored, I counted 17 billion ants in my backyard. Now, we're going to convert that into scientific notation. Now, in order to do that, I have to see if I can get the writing instrument, but I'm struggling to get my little pen. Let's see about this pen. We'll pick a good color and red. We know that there's a decimal point right here, even though we can't see it. Not written, so a lot of those zeros, in fact, none of those zeros are significant. Only the 1 and the 7 are significant. We really need to use these significant figures in the coefficient. So I'm going to move them right over here. 1.7. We can't have a 17 because in science class, in chem, the coefficient has to be 1.7, greater than 1, less than 10. Now the decimal point is over here, but it needs to go between the 1 and the 7. It has to go 3, 6, 9, 10 places. So in order to make 17 billion into 1.7 times 10 to the, it would be 10 because the decimal place moved 10 places. 3, 6, 9, 10. And then of course, ants, right? I was going to draw a little picture. Ants have 6 legs. And actually, that's not a very good unit, right? 6 legs, but the unit is ants. You can't really have that. Let's see if I can hide all my, I don't remember how to clear. Oh, it's down here, clear all my drawings. So we get it right. Now this next one, I think this is the diameter of the Earth. I looked it up and I picked a number. This one has 4 significant figures. We're going to have to put all 4 significant figures in the coefficient. So we're going to start out with 6374 in the front. but we have to turn that into a decimal because we can't have 6,374 in the front coefficient. It has to be greater than 1 but less than 10. And when we do that, it's going to be 6.374, and the decimal is going to move from this invisible place where it's invisible at the end of the 0. It's going to move over 6 places, and it's going to become 6.374 times 10 to the, ooh, look at that. There's a boo-boo. I'm going to fix that right now as we stay here, and I'll hit save, and then we'll view from the current slide, and voila, it's fixed. Sorry about that. Number 77 is a small number. This is a very, very small number, 34 thousandths of a gram. This is a less than 1. We're going to have a negative exponent. So we're going to have to start with 3 and 4. Those are the two significant figures. And I have to put the decimal between them because with 3 and 4, it can't be 34. It can't be 0.34. It has to be between 1 and 10. Now, the decimal is right here, but I want to move it over 2 places. But I'm moving it 2 places to the smaller. So this is going to be times 10 to the -2 grams. This is going to say 3.4 times 10 to the -2 grams. The decimal place moves 2 places to the small direction. Now this next one, here's the decimal way over here, but this is where it belongs, because when we look at this tiny number, we have to turn it into a number that has 1.54 as a coefficient. So I'll just write the 1.54 first. And now I got to see what's going on. I got my decimal over here. I got to move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places, but it's really, really small. It's not to the 10th power. It's going to be times 10 to the -10th meters. Now, this crazy small number, I think, is the diameter of a carbon atom. Super ridiculously small. But these are numbers we deal with in chemistry, and we need to be able to mathematically deal with them. And we don't want to deal with these crazy decimals, or like in number 75, these gigantic numbers that really don't fit in the calculator. This next one, 0.0083, we're going to have to get it down to 8.3, right? 8.3. The decimal is, of course, way over here. You can see it, and we want to put it over here. So it's going to go in a 1, 2, 3, 4, 5, 10 to the -6th places, 10 to the -6th meters. This is another really small thing. I forget what it is, but we're just manipulating the decimals and turning them into scientific notation. Now, this is a gigantic number of years. This is actually probably longer than the universe has been alive. But it's just math right now. It's just, can you figure it out? The front is going to be 4.5, right? Because those are the only significant figures. The decimal is here, but it's invisible. I'm going to move it over 3, 6, 9, 12, 15, 18, 19, 20, 21, 22, 23, 24. So it's going to be times 10 to the 24th years, which of course is crazy. Let's see what we got going on with the answers. I'll get rid of this writing stuff. We got 3.4 times 10 to the -2nd, 1.54 times 10 to the -10th, 8.3 times 10 to the -6, and then this crazy one, which is truly just, I don't even know why I wrote that. Can't possibly be that long. That's longer than the age of the known universe. So you can make really big and really small numbers into scientific notation. It's going to make your math easier. Now, we got to convert these into numbers. Now, in order to do this, we're going to look at the coefficient. The coefficient here is 6.02. And so we're going to write 602 without a decimal. The decimal is right here, but we got to move it all the way to the right. We got to add a lot of places. Now we have to move the decimal 23 places. So we moved it 2 places already. That means you got to have 21 more zeros here. Now that's a ridiculous number of zeros. I'm not going to write them. So I'm going to clear this drawing. I'm going to get rid of that, and we're going to look and see what it looks like. 602, and then 3, 6, 9, 12, 15, 18, 21 more zeros. This, of course, is the number of atoms or molecules in a mole of atoms or a mole of molecules. You could have a mole of hard-boiled eggs, I suppose, but it'll be bigger than the Earth. A mole is just a scientific unit, and this number will come up a lot. And again, it's called Avogadro's number. He was Italian, and rather than go into the pizza business, he went into chemistry, and they named the number after him. Now, this next one, 3.5 times 10 to the 4th, you're going to write the number 35. As soon as you write the number 35, you've moved the decimal from 3.5 to 35, so you have to add 3 more zeros after that because you only move it 4 places altogether. 3.5 becomes 35, that's 1 place, and then 3 more, and it becomes 35,000 grams. And that sounds like a lot, but actually grams are pretty little. An aspirin might be about 1 gram, approximately. Grams are not too big. Next one up. Now this one's a little tricky. I'm going to actually write this one for you because it's a little trickier. We're going to have to start out, and we have to see first, look, this is a negative. So it's going to be a decimal. I'm going to start over here with 125 because those are the significant figures. Now we have to move it 7 places. It used to be 1.25. I already moved it over 1 place. So I have to go 6 more zeros. So I'm going to go 1, 2, 3, 4, 5, 6. Now I put my decimal in, and my rule for me, I always put that extra 0 in because then I know, hey, I'd be paying attention here. It's not just like I forgot the number. No, it's a 0 point. And that 0 on the left is not significant, and none of these zeros are significant, only those 3 right there. So let's see if we get this one right, and I'm pretty sure I got it right. Look at that. Now this next one, it's got 4 significant figures in the front, and it's times 10 to the 3rd. So we have to move this over 3 places. Well, if we move it over 3 places, look what happens, just like that. And this, actually, there's a mistake in this also, and I'm going to fix it right now as well. This should be a decimal right there, and I'm even going to color it blue so that we'll see it. All right, and let's see, slideshow from current slide. Now, these slides are from last year, and in all honesty, when I'm doing this live, I really think sometimes I put these mistakes in on purpose just to see if anybody's paying attention. But now it's a little different, and I'm making them perfect. So there was a little boo-boo. In order to keep 4 significant figures, it really needs to have another decimal like that. All right. One of these random questions. We have to convert 36.8 kilograms into ounces. And then your answer has to be given in scientific notation. Then you have to round to the correct number of significant figures. So there's a lot going on in this, right? And you don't know a lot of these conversions probably. These hints, 454 grams is a pound. That's written on every single pork and bean can in America. That's a good number to remember. And 1 pound happens to also be 16 ounces. So the 3 of those things are all equal. 454 grams, 1 pound, and 16 ounces. And then, of course, a kg, a kilogram, is equal to 1,000 grams. Now, with these conversion factors, or their equalities, you can make conversion factors, we should be able to get through this. Now, our starting point, of course, is 36.8 kilograms. And we put it over 1 so that we realize that the kilograms are actually in the numerator. They are in the numerator, but now they are in the numerator. And the first thing we're going to do is we're going to convert from kilograms to grams, and we should get our pen out, and then we could cancel the kilograms like that, and now we have grams. And if we put an equal sign, we would get the answer in grams, but we don't want it in grams, we want it in ounces. So we have to go from grams, which is metric, to English. So we have to switch now from grams to metric. So I'm gonna say, hey, look at this. This many grams and this many ounces are equal. So I'm gonna do this. I'm gonna say there's 454 grams that I can put in the denominator, as long as I put something like 16 OZs in the numerator. Now, again, I've talked about this, but I'm going to say it again. 16 over 454 does not equal 1. But with the units, 16 ounces equals 454 grams. It's okay. It does equal 1. So we're just going to multiply by 1 again, and all we're doing is converting and churning those units from one unit to another. Now, the grams in the numerator cancel the grams in the denominator, and that's good. Now we have ounces, and that's what we want. So you could put an equal sign. Okay? Good. Now I'm going to X out of this. And unfortunately, I think I did it differently in this next picture. I have to figure out how to get rid of these drawings. I want to clear my drawings, clear all drawings. And there's different ways to do this, but we'll see what happens on the next slide. Oh, look, I went from kilograms to grams, then I did grams to pounds, then I went from pounds to ounces. But that's still all the same. The 16's on the top with the ounces and the 454. So to do it this way, I took an extra step. Instead of doing it in 3 steps, I did it in 4 steps, but we get the same exact answer. You multiply across the top, and you get this big number, 588,800. Across the bottom, you get 454, and that's what the answer is. Now, this becomes tricky. 1296.9, but you can only round to 3 significant figures. So the first thing you do is you keep the 1 and the 2, but then the 9 makes it round up, so it's got to be 1 and 3, and then what? Well, you got to keep 3 significant figures. You're going to have to round to 1.30, 1300. 1300 only has 2 significant figures, and if you make it 1300 point, that's 4 significant figures. So you're going to have to work it out with scientific notation. All the units are going to cancel. Now, this is also important that you need to see at the beginning of this, there are 3 significant figures, 3 San Franciscos, and then here, unlimited because it's an equality, unlimited because it's an equality, unlimited because it's an equality. Here, this is just a calculation. We're not going to round anything. We're still calculating. Then this becomes the answer. And then it really should be, it really needs to round to 1300. But 1300, that doesn't have the right number of significant figures. It's just 2 significant figures. So in order to round it to the closest best answer, you're going to have to turn it into scientific notation and make it 1.30 times 10 to the 3rd. All right. Now, some people can hold their breath for a long time. I can hold my breath underwater for 25 or 30 seconds. I'm getting old. Maybe a minute when I was a kid. 300 seconds is like a real kind of a record. 300 point seconds. First of all, it's 3 significant figures. Second of all, it's 5 minutes. I mean, this is a long time. This is not normal. Don't try to do this. But if you had to and you wanted to just do the math, converting 300 seconds into years, how long could the world record holder hold his breath in years? This is a wacky thing to do because 300 seconds is normal. Nobody holds their breath for a year, and the decimal of a year is going to be super duper small. But mathematically, you can do this. What's your starting point? You got to start with the starting point. You're going to have to start with 300 point seconds over 1, 3 significant figures. And the first thing you could do is convert seconds into minutes. I'm going to wait now. Seconds into minutes. Then you could do minutes into hours, hours into days, days into years. And as soon as you get years in the numerator, everything else cancels out. Then you got to do the math. So take a minute. I'm going to wait here. I'm going to drink my seltzer. It's peach seltzer. Comes in an aluminum can. Aluminum is number 13 on the periodic table. Aluminum has 13 protons, and it also has 13 electrons. Protons are positive, electrons are negative. Tricky business. It has 14 neutrons, but that's way too complicated for right now. If your element number 13, you have to have 13 protons. That's what it means. And if you have 13 positive protons, you have the same number of negative electrons. Neutrons are funky. Okay, back to this problem. We're going to see what happens now. We're going to go from seconds get changed to minutes. Then minutes get changed to hours. Then hours get changed to days. Days get changed to years. There it is in top. All the other units cancel out. Stop, put the equal sign, the most important symbol in mathematics. Multiply it across the top. It's supposed to be, I got to fix this slide too. Look at this ridiculous silliness. It's 300 point. And I'll hit save and from the current slide. And I think I'm going to have to check my math because that was a mistake there. And I will do this 300 divided by 315,360,000. 315,360,000 equals 0.95. Oop, I'm going to change this too. I mean, I have a better calculator. I did this the last time, I know, on a blue one. And it's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. The rest of it's right. Now, if you did this on a little tiny calculator, the answer comes out to be 0.000095, and you can't see the next number. I just did this on my iPhone, and my iPhone spreads out a little more, so it's actually not 9.5. It's not 9.50. It's 9.51. All these units cancel. This, of course, is called dimensional analysis, or it's called unit conversion math. And the answer is changed to scientific notation. All right, we're going to use scientific notation in different ways. We're going to multiply with it. Now, multiplying and dividing actually really easy. I got to hang on 2 seconds here. All right, I'll be back in 1 minute. Be patient.
Want me to take over?
Yeah, take over. Sit down and just look. Don't keep anything.
Okay, so I'm going to help you understand this. Not really. Well, actually, I could, but I won't. This is a moment to think about what is the meaning of life? Okay. You're thinking about what the meaning of life is.
Oh. All right. My laptop wire got all tangled. My wife is crazy. All right. The rules for multiplication are really easy. You're going to multiply the coefficients. Then you're going to add up the powers of 10. And sometimes your answer just pops out and it's beautiful, like for 87. But sometimes with 88, we're going to see it's a little tricky. There's one extra step. You might have to adjust your answer. So let's see, 87. You got 3 times 10 to the 5th times 2 times 10 to the squared. The coefficients are 3 and 2. What's 3 times 2? 3 times 2, come on, 6. So it's going to be 6 times 10 to the, what's 5 plus 2? Look at that. Oh, I got the answer for the next one too. How'd that happen? All right, now for this next one, 5.0 times 3.0, that's going to be 15. 5 times 3 is 15 times 10 to the 6th. We can't have 15. We have to change that to 1.5. Now, if I make my coefficient smaller by 1 decimal place, I got to make my answer exponent 1 place bigger. So it changes from 15 times 10 to the 6th. It gets adjusted to 1.5 times 10 to the 7th. They switch 1 place. The coefficient gets smaller by times 10, and the exponent gets bigger by times 10. 15 times 10 to the 6th equals this, but it's not the right answer. Because in chemistry, the rule is the coefficient has to be greater than 1 but less than 10. Now, for division, division's easy too. Divide the coefficients and then subtract the powers of 10. Now, honestly, if you have an iPhone or you have one of those fancy black calculators, the Texas Instruments one, and you know how to use all those parentheses and stuff, you could probably just push this through the machine and the answer will come out. You can't use a programmable calculator on the regions, and you really should understand the mathematics behind this, but here we go. 89, 3 divided by 2, 1.5. And then 10 to the 4th, 10 to the 2nd, you have to subtract. So it's going to be 1.5 times 10 squared. Now on the other side here, the answer already popped up. 9 divided by 3, 3. And then 10 to the 5th compared to 10 to the 3rd, 5 take away 3 is 2. So the answer is 3.0 times 10 squared. No adjusting this time. The coefficients are greater than 1, less than 10. You don't have to adjust them. It was easy. It was easy. Now, this one's harder. Addition and subtraction is one extra step. Now, when you look at this question here for 92, both of these numbers have 10 to the 7th. But if you look at number 93 in blue, we have 10 to the 8th plus something to 10 to the 6th. Now, the problem with this one is they look nice, but if you think about it, the top number it's going to be 62 with 7 zeros, but the bottom number is going to be 15 with only 5 zeros. So the 6 and the 2 on top are not really lined up. They're in different columns, and it's hard to see. So for addition and also for subtraction, you have to make sure the powers of 10 match, and then you add the coefficients, then you add the coefficients to keep the powers of 10. So for 92, 6.5 and 2.2 is 8.7. You just add them up. 5 plus 2 is 7, and then the next 6 plus 2 is 8, and you keep it at 10 to the 7. But for 93, you have to choose which one of these you're going to do. I'm actually going to do this one with my pen, if I can make it come back. It doesn't always come back too quick for me. I don't know why. You have to decide, do you like 8s or do you like 6? Now, it doesn't matter which you choose. They both got to be the same. So I'm going to pick 10 to the 8th because it's already there. 6.2 times 10 to the 8th. I'm going to leave that there the way it is. That's an 8. It's a little sloppy. On the bottom, I got to switch this to also being 10 to the 8th. But it's not really 10 to the 8th. Look, I made the exponent 10 times 10, 100 times bigger. Now, if I make it 100 times bigger, I got to make the coefficient 100 times smaller. So temporarily, I got to break my rule about my coefficient. I have to make this 10 to the 6th 2 places bigger. I have to move this decimal place 2 places over. So I'm going to add 0.015. And you see, of course, how these decimals are not really lined up, because 10 to the 8th and 10 to the 6th are not really lined up. They just look pretty in blue because I typed them orderly, but they don't really belong there. You have to make sure you have these coefficients in the right columns, and you have to make sure the powers of 10 add up. So now when we add this up, this is going to be 10 to the 8th, and this is going to be 6.215 times 10 to the 8th. Now, I can only have 2 significant figures. We got to keep track of that too sometimes. So it's going to have to be 6.2 times 10 to the 8th is the answer. And I'm going to change my font because I want to say, look at this number, and then we added this, and look at my answer. What the heck is going on? What the heck is going on? Now, we started with a number, we added another big number to it, we got the same exact numbers we started with, like we didn't add anything. How do we explain such a crazy thing? Well, the numbers are cute. They're little things right next to each other. But 10 to the 8th is a number that's more than 100 times. 6.2 times 10 to the 8th is more than 100 times bigger than the second number. So this is kind of like, say you have $62 and you find a penny and a half. There's no such thing, but you find a penny on the floor and you add it. How much money do you have? You could argue that you have $62 in a penny, but really, you have 62 bucks. Who are you kidding? You're not going to impress anybody by saying, I have $62 in a penny. When you have this really big number times 10 to the 8th, and you add a much smaller number, and you have to worry about your significant figures, sometimes you added something that's so small, you're kind of like, you round it away, right? If your name is Bill Gates and you have billions and billions of dollars, and you find $400 bills on the floor, put them in your pocket till later. If you found four $100 bills, it would change your day. Bill Gates, he might not even pick them up. He might say, who can I give this to? He's got so much money. Did it change his net worth? Can hardly calculate it. Here we added a big number to a smaller number, and it rounds to be the same number. So sometimes that's what happens. You get something that looks like you're doing something, but really it's just math now, and adding such a small little number, it doesn't really make a difference. Kind of cool. But the rule, ready? Make sure the powers of 10 match, then you're going to add the coefficients and keep the same power of 10. Are you getting this? We're almost done. We're up to 92. We only got to get to 100. Subtraction rules. Same rule, kind of. Make sure the powers of 10 match, but then you subtract and keep the same power of 10. And if you have to, you got to make an adjustment. So let's look at 95. They're both 10 to the third. So all you got to do is say 8.5 subtract 2.4. It's going to be 6.1 times 10 to the third. It's no problem. That one's easy. The other one, you got to figure it out. Let's see what I did. Oh, there we do. Now the second one needs to be adjusting. And I forget in the next slide which way I went. You can make them both 10 to the fifth, which means it will be 7.1 times 10 to the fifth minus. Now, if we make the exponent bigger, we got to make the coefficients one be 0.16 times 10 to the fifth. Or maybe I did it the other way. Oh, I didn't. I made them both 10 to the fifth. So here it's 7.1 minus 0.16. It becomes 6.94 times 10 to the fifth. And then it's going to round to 6.9 times 10 to the fifth. Watch the rule. Powers of 10 match, subtract the front, keep the powers of 10. And sometimes you got to make a little adjustment. We didn't have to adjust these. Here's two math problems. I'll drink some more seltzer. Get to work. You're going to have to make these both 10 to the 11th, or the other one both 10 to the 14th. So whichever one you choose. Doesn't matter if they're bigger or smaller. In the end, you either make an adjustment or you don't, but you're going to get the same answer. You're adding or you're subtracting. These are the hard ones. Take a break. I'll wait for you. Go ahead. Let me tell you a story. It's very important in chemistry that you never, ever listen to atoms. Atoms are liars. They make up everything. I hear you laughing. Some of you smarter kids, right? You're laughing. Some of you are giggling because you think it's funny. You're not really sure what it means. Atoms make up matter. They make up everything. It's a little joke. All right, let's see what we got. 97. I made them both 10 to the 11th. So the top number, 8.72 times 10 to the 11th, that's going to stay. There's no problem. But if we make the bottom number there, 10 to the 10th, make it 10 to 11th, that goes up. We got to make the other one go down by 10. We got to move the decimal the other way, and then we just add them up. And then we got to check significant figures. Three significant figures, it becomes 8.89 times 10 to the 11th. Three significant figures. Now, for the next one, you have to choose. And again, I forget which one I chose. Let's see what I did. I made them both 10 to the 15th. So the bottom number, 2.25 times 10 to the 15th, that's fine. The top number, I made the exponent 10 times bigger. I got to make the coefficient 10 times smaller, and I make, instead of 4.65, it's 0.465. And now I got to subtract. Okay. 0.465 minus 2.25 happens to be a negative number. That's okay. Four significant figures there. You can't have that. You got to go to three significant figures. So it's going to be negative 2.03 times 10 to the, oops, another mistake. Who is making these slides? Who can I hold responsible for all these boo-boos? Listen, make mistakes. The more you try, the more you're going to make mistakes. Don't be afraid to make mistakes. I make them. Look at me. I didn't even break a sweat. I had to go put the weed whacker battery on the weed whacker for my wife and let her sit in here for, you think that's not a mistake? Who cares? Here we go. Last two problems. Then we're taking a break. There's Avogadro's number. We're going to multiply. You're going to need a calculator for this. 6.02 times 1.5. That's a hard one to do. It's going to be 9.03. And then it's going to be adding them up. 10 to the 23rd plus 2 times 10 to the 25th. So it's going to be I think it's going to be 9.03. We'll see. And then the bottom one, 9.05 divided by 3.2, you got to have a calculator. And then it's going to be 10 to the 19th minus 10 to the 16th and 10 to the 3rd. And look at this. It's so easy. It's so easy to fall in love. It's so easy to do exponent math, okay? This is it. You did great. This wasn't fun. Some of the classes, I can't make them too fun. This is math. You got to know it. You should have known it. Maybe you didn't know it. Maybe you do know it. Hopefully you know it again. If you didn't understand any of this, you have to ask me, right? You just come into one of the Zooms first period, or when you come into school, raise your hand and say, what the heck is going on here, Charlie? Don't call me Charlie, though. Or you can send me an email. I don't understand this. Or you can call me on the phone and say, can you turn this on and we can look at this problem together? And I will talk you through it. I will keep doing this. I will do this as many times as you need me to. I love this. I get paid for this. I'll show you my paycheck. My first paycheck's coming. I think it's coming this Thursday. I'll show it to you. I get paid 0.00. I love this so much I do it for free. That's not true, but I would. Well, if I could, I would. If I was as rich as Bill Gates, I would do this for free because I freaking love this. I love chemistry and I love being a teacher. I love my wife. You saw her. Hey, that's Janet. I've been married for a long time. All right. Thanks for watching. Over and out and goodbye. Stop.